Okay, so for this three-phase problem, the first thing, like all of these, is that we want to read it and make sure that we know what it's talking about. That key word right there, which everything in this class will be balanced because this is 301, but that makes this actually a pretty simple problem. It's a balanced Y-connected generator, which is this thing right here. We said that these are inductor coils, but that you can think of each of these as being like its own AC source that we've been doing the whole time. And it has a Y-connected load on this other side. It's shaped like a Y, it's a Y. This point that's neutral, similar to how we had grounds in our single phase this whole time, this neutral we can think of as kind of like that ground that connects these 2 points with a wire. And what that allows us to do is to draw a single phase equivalent. So if this is my source, the first step that we're going to do is solve for the phase voltage EAN to make that like the source. So we take the line voltage, 208 angle 0, divide it by, and this is on the formula sheet, divide the line by √3 angle 30. We solve it through 120 volts angle -30. So I can turn this complicated looking thing into this simple single phase. VAN is that same as EAN. 120 volts angle -30 is my new source. There's the point A right there. And it's like I have just this tiny simple circuit. I can solve for the other phase voltages as it asked me. If the line voltage is this, calculate the phase voltages. And all I do is I change it by this -120 and +120. And I said, if it doesn't say otherwise, you can assume a positive phase sequence, which means that A, the phase of A, -120 for the B, and the +120 for the C. I can do my line voltages. The other line voltages, it's 208, and we change it. It's a balanced system. We change it by 120, change it by 120, and that's it. For the last part is the line currents, and what we said was that we have a single phase equivalent. So for a single phase, the single ZAN is just 20 minus J15. 20 ohm resistor, 15 ohm capacitor, so we still have the minus J, and it's like that's what's inside this box on this side. Note there are no line impedances between big A and little a. Big A and little a, there's no line impedances. If there was, then whenever I did my current and I did V equals IZ, then I would have to just include that Z in my Z total. As it is, V equals IZ, favorite law. So I take 120 volts divided by 20 minus 15J, and I get a current of 4.8 angle 6.87. The currents are also different phases, and it's shifted by just exactly -120, +120. So the math on these is actually super easy. It's just this matter of turning a complicated looking three-phase system into a very easy single phase. And the main thing that you need to remember is the words line versus phase. Line voltage versus phase voltage, VAN or VAB. Whereas if we were talking about the currents, it's going to be the same current. And that makes sense when we look at the single phase equivalent. The current coming up through here is the same as going through the source. This line current is the same as the phase current, is the same as the phase current on this side.